SwayamPrabha.
So in the last class, we have seen a faster FPT algorithm for vertex cover, and we have also seen the definition of kernelization. So in today's class, let's understand let's see an example of a kernelization algorithm. Algorithm for vertex cover. So let's do some easy pre-processing rules. So in kernelization, they are called reduction rules because we are reducing the size of the instance. The first reduction rule, one is delete isolated vertices, that is vertices with degree 0. So clearly the new instance is equivalent to the old instance. This does not affect the size of the minimum vertex covered because isolated vertices does not belong to a minimum vertex cover. Reduction rule 2, for every vertex or let V be a vertex with degree of V greater than equal to k plus 1, at least k plus 1 edges incident on V, then any k size minimum vertex cover must pick V, because if it does not pick V, it has to pick its neighborhood whose size is at least k plus 1. So then return G minus V, pick V, and the budget becomes k minus 1. Okay, now we claim that the number of vertices and number of edges must be small. So now we claim, so we keep applying reduction rule 1 and 2 repeatedly. So maybe at the beginning there is no isolated vertex, but after applying reduction rule 2, there some isolated vertex is created. So then again the isolated vertex we delete, and we keep doing this when we keep applying reduction rules 1 and 2 whenever any one of them is applicable, and when both reduction rules 1 and 2 are not applicable, the graph has the graph, the instance is a no instance if it contains more than k square edges. Okay, of course, if k becomes negative or 0 and there is some isolated some edge, then uh, then the instance is a no instance. So we can write it here, reduction rule 0 if k equal to 0 and the graph contains any edge, return a no instance. Recall, a kernelization algorithm does not solve the problem, it outputs an equivalent instance. So in this case, if k is 0 and there is some edge, then the instance is a no instance, and it creates output simply some trivial no instance, maybe a graph with two vertices and the edge, and the budget is 0, something like that. Okay, so proof. Since reduction rule 2 is not applicable, is not applicable, the maximum degree of the graph is at most k. Now vertex cover of size at most k then can cover at most k square edges. Then because the degree of every vertex is at most k, then any subset of k vertices can cover as at most k square edges. Hence, if the graph has more than k square edges, then it must be a no instance, which concludes the proof. So you see that this algorithm, this kernelization algorithm runs in polynomial time. What is that algorithm? Keep applying reduction rule 0, 1 and 2 if any one of them applicable, and if they are not applicable, at the end if it has more than k square edges, then again output a dummy no instance, and if it is less than k square edges, then output that instance. Okay, so next we see that no, really this kernelization is just the other side of the coin of FPT algorithm. What do we mean by that? So here is a theorem. For suppose there exists an algorithm need not be efficient for a parameterized problem pi, then there is an FPT algorithm for pi if and only if there exists a kernelization algorithm for pi. Proof. So in if direction, so suppose there exists a kernelization algorithm A AK for pi. So using this we will design an FPT algorithm for pi. So let x comma k be an arbitrary instance of pi. What we do is that we first apply the kernelization algorithm on AK to create an equivalent instance. We apply AK on x comma k to obtain an equivalent instance x prime comma k prime where size of x prime is less than equal to g of k for some computable function g. Now what we do is that now we use the assumption that there exists an algorithm, need not be efficient, need not run in polynomial time, but there exists an algorithm for the problem. So we apply that algorithm. Now we solve the algorithm, we apply the algorithm for the problem to solve x prime comma k prime. Okay. The runtime of our overall algorithm of our overall algorithm is, first we applied the Kernelization algorithm, which took poly n time, which is a polynomial time algorithm, plus then we apply maybe brute force algorithm, which run in say f of n time, but the size of the instance is g of k, so f of g of k, where the algorithm for the problem pi takes f of n time. However, the runtime is not exactly in FPT form, it may appear, but f of poly n plus f of g of k is big of f of g of k times poly n. Hence, we have an FPT algorithm for pi. So, if part is done. Now, for the only if part. For the only if part, means suppose that we have an FPT algorithm, then we will show that there also exists a kernelization algorithm. For the only if part, let AF be an algorithm for pi which runs in time big of f of k times poly n for, or made this way, time at most f of k times n to the c of time at most this for some computable function f. Okay. Now, what we do is we compare n with f. So, what we do is, we run AF for n to the c plus 1 steps. if AF terminates within n to the c plus 1 steps, then we have solved the instance. X comma k, and once solved we can always output accordingly. If the instance is found to be yes instance, we can output a dummy yes instance, and if the instance is found to be a no instance, then we will output a dummy no instance. Okay. Otherwise that means if AF does not terminate within first n to the c plus 1 steps, then we simply output x comma k. Now we claim that this algorithm is a kernelization algorithm. So two cases: if size of x, which is n, size of input instance, if this is more than f of k, or if this is less than f of k, then AF, the FPT algorithm, how much time it takes? It takes at most f of k times n to the c, and f of k is at most n. Then AF terminates within n to the c plus 1 steps. Why? Because it takes at most f of k times n to the c steps, and f of k is at most n. So f of k times n to the c is at most n to the c plus 1, and in this case, hence the output instance is small, because we will be outputting, we are solving the instance, we have solved the instance, and we will simply output a dummy instance of constant size. So in this case, the size of output instance is big O of 1. Otherwise, we have size of x, which is n, which is greater than f of k. In this case, algorithm may not terminate, but if it does not terminate, then what will we output? We output, what is the size of the output instance? The size of the output instance is x only, the same instance we output, and x is, size of x is n, and which is greater than f of k. In this case, the algorithm outputs x comma k. However, we have size of x is sorry, if f of k is, I think this will work if f of k is less than equal to n. If f of k is less than equal to n, then only f of k times n to the c is less than equal to n to the c plus 1. And the other case is n is less than f of k. If n is less than f of k, then f of k times n to the c is need not be less than equal to n to the c plus 1. So hence, but in this case we have a size of x is less than f of k. Of course, k prime is the new parameter which is same as k. So hence we have kernelization algorithm for pi which outputs a kernel of instance size at most f of k and parameter is bounded above by k. Moreover, f is a computable function by the assumption of FPT algorithm AF for pi. Okay. So this concludes the proof. Hence, to design an FPT algorithm, there is also an alternative technique to design a kernelization algorithm. And for some problems, the best FPT algorithm known is via this route. That means we design a kernelization algorithm, and if we design a kernelization algorithm, here whose output kernel is f of k, and typically if the problem is in xp, that means there exists a algorithm of n to the k time, then we can fit that, and using that we can design an FPT algorithm. So this shows that if we want to design a kernelization algorithm, we can as well design a FPT algorithm, and vice versa. To design a FPT algorithm, it is equivalent to design a kernelization algorithm, but the runtime may be different. As we have seen, for vertex cover, the same search tree based technique, but by applying more clever technique, we are able to reduce the runtime of the algorithm for vertex cover from 2 to the k to 1.46 to the power k. So let us stop here today. So in the next class, we will see some more examples of FPT algorithms and kernels.